Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about Hasse's local global principle, which provides a framework for studying Diophantine equations in number theory. So to introduce this Hasse principle, I guess it's best to phrase it in terms of Hilbert's 10th problem. But before I go on and state Hilbert's 10th problem, you may wonder, why does Hilbert have a 10th problem? So let me tell you about this story. So Hilbert, of course, was one of the towering mathematicians of the 20th century. And in 1900, he gave an address to the International Congress of Mathematicians. And in the address, what he decided to do, rather than talk about his work, he decided to present 23 mathematical problems that he thought were the most important problems of his time. And it turns out that each of these problems have really given rise to a lot of interesting mathematics in the 20th century. And the 10th one concerns number theory. So that's the one I want to tell you about today. I guess I won't phrase it the way he did it. I'll choose a version of it, and I'll choose the projected version, which involves some polynomials with coefficients in integers in variables x0 up to xn. And since I'm looking at the projected version, I'll assume these polynomials to be homogeneous. So for each of these polynomials, the degrees of each of the terms will be the same. And so his 10th problem can be stated as follows, okay? We want to basically find the common zeros of all these polynomials. Since these are homogeneous, they'll always have the zero solution, but we want to look at non-zero integral solutions to this. And we look for these non-zero integral solutions, and we want an algorithm to see whether you can find such a solution or not. Now, it turned out that he presented this problem in 1900, but it wasn't until the 1970s that was actually settled. And the answer given by Matijasevich is rather interesting. His answer was that actually no such algorithm exists. None exists. So this is rather interesting fact. You can also look at an analogous version of this and try to solve for rational solutions. And what's interesting here is that over the rationals, if you look for rational solutions, non-zero rational solutions, then the analogous problem is actually open, so we don't know the answer to that. Okay, so what should we do? This is a bit of a conundrum. We don't have an algorithm to tell us if there exists solutions to such a set of equations. But one thing we can do is to try to look at the analogous local problem. Okay, so let me just set up some notation before I go on to state properly the local problem. So suppose you have a field F. So we can look at the set of non-zero solutions to these equations over F, and we'll look at them up to scalar. So that corresponds to the projective variety. I mean, the up to scalar won't be too important for us, since we'll only be interested to know whether this set is non-empty or not. Okay, so we'll look at the set of solutions to those equations up to scalar. So looking at local problems means that we're not looking over for rational solutions, but we're going to look inside the p-adic rational numbers instead. And the thing that we do know, this is the key point, is that if we have rational solutions which are non-zero, we get solutions in the p-adic rationals which are non-zero as well. Okay, so to a certain extent, since we have this implication, this should be an easier condition than this condition here. So checking for solutions which are rational, okay, non-zero rational solutions, should be harder than checking for all these local solutions. Okay, and the rather interesting fact is that if you look at these local equations instead, this local problem, then if you want to determine whether all of these projective varieties are non-empty, in other words, whether there exist p-adic rational solutions for all p, and you want to do this for all p simultaneously, you can actually decide whether that's such a solution exists or not. So that's a rather interesting fact, which is very different from what you see over here. In this case, the integer case, the global integer case where no such algorithm exists. And in this case here where you look at global rational solutions where the problem is still open. So it's presumably quite hard. So why is it that we can check for existence of local solutions? In other words, solutions over all these p-adic rationals. Well, to tell you the reason, I just need to give you some basic facts. So the first one is, well, if you take p to be infinity, then remember q hat infinity is the real numbers. And checking solutions over the reals actually is decidable, and that comes from work of Tarski and Zeidenberg. Okay, so what about the other primes p? Okay, so the finite primes. How do we check for local solutions over the q hat p? Well, the first thing that you do is you check over the finite field fp. And the thing about that is that in this case here, since the field is finite, the number of inputs that you can put in is finite, so this is just a finite problem. So it's very easy to check whether there exist solutions over finite fields. And once we have the answer over finite fields, the point is that Hensel's lemma now comes to the rescue and allows us to lift solutions over finite fields to solutions over the p-adic rationals. So a lot of the time you can reduce the question over q hat p to just the question over fp. And then there's only one more thing which is rather interesting. So it seems like checking local solutions for each individual p is not too bad, but of course you need to check this for all primes simultaneously. And so how do we handle a large number of primes? Well, the key point is that there are some estimates due to Langevin which tell you about solutions over the finite fields for many primes simultaneously. And what more precisely it does is it shows you that there exist solutions over finite fields fp for all p above some certain determinable bound. So once you have this as non-empty, it's quite easy to show that for most of these q hat p, you'll get non-zero solutions. And so there are a few values of primes for which you need to check. And those few values of those primes, you can check individually because it's essentially a finite problem here plus using Hensel's lemma. So that's the reason why the search for local solutions is actually decidable. Okay, so where do we go from here? So really, looking for local solutions is an easier problem than looking for global solutions, and it gives us a way to approach Diophantine equations. And the way we do that is via something called Hasse's principle. And that's suggested by the things that we've looked at. So remember, the main thing that we have is that if we look for solutions, global solutions, and we find a global solution over Q, then we get local solutions over Q hat P for all primes P, including the infinite prime P, in other words, including over the reals. And there's a theorem due to Hasse-Minkowski which actually tells us that sometimes the converse is true too. And when does the converse hold? It holds when you've just got one polynomial f, and that's a quadratic. So if you have a quadratic form, f in variables x0 up to xn, how can you check whether it has a non-zero solution over the rationals? Well, all you need to do by this theorem of Hasse and Minkowski is check that it has non-zero solutions over all the p-adic rationals, including where p equals infinity, so including over the reals as well. And the good thing about this criterion here is that it is actually a decidable thing by the result that I mentioned before, and basically these facts here. So this gives us a way to study Diophantine equations. So this is how you should think about Diophantine equations. The first thing you should do is you should try to check to see whether you have local solutions, because that's something that is at least decidable. Okay, so you might ask, well, how often does this condition occur? How often is it that to check for the existence of global solutions, you just need to check for local solutions? Well, that's a good question, and what we'll do instead is we'll turn it into a definition. We'll say that to check for the existence of a global solution, all you need to do is to check for local solutions, okay? For those cases, we'll say that the Hasse principle holds, because you get a theorem like the Hasse-Minkowski theorem. So more formally, suppose you have those homogeneous polynomials f1 up to fr. We can use that to define a projective variety V. And we say that this projective variety V satisfies the Hasse principle if the fact that there exist local solutions for all these q hat p, for all p, including the infinite prime infinity, implies that there exists a global solution over q as well. So a very natural question to pose here is, which varieties V satisfy the Hasse principle? Because if it satisfies the Hasse principle, to check that there are global solutions to those equations, you just have to check that there are local solutions, and that's something which is decidable. Okay, so what I want to do here is to actually give you a counterexample, which is quite easy to see. And to give that counterexample, I need a little lemma. So hopefully this is familiar to all of you. Suppose you look at the finite field Fp, and you look at the multiplicative group of non-zero elements in there. So this group, this multiplicative group, is actually cyclic. So since it's a cyclic group, what can we do? We can look at the set of all squares inside here. That's a subgroup. And when you look at the quotient, since this is cyclic, it's actually isomorphic to the cyclic group with 2 elements. Okay, so this is a very, very important fact, that this multiplicative group, if you mod out by the subgroup of squares inside here, then you get Z mod 2. And what does that mean in particular? It means the following. Suppose you have 2 non-squares inside here. Okay, so if you have 2 non-squares inside this multiplicative group, then inside this quotient, the product will be trivial because they correspond to, I guess, the addition of a 1 with 1 here, which is 2, which is congruent to 0, mod 2. So since it's trivial inside here, it's trivial inside here, so that must be a square. So that means that if you multiply 2 non-squares inside this multiplicative group, it will be a square. Okay, so let's come up with a simple counterexample to this Hasse's principle. I'll give an example here which is affine, which means it's given not by a homogeneous equation, but just an ordinary polynomial equation here. Okay, it's quite easy to get a projective example. I'll tell you about that later, just by homogenizing this. So here we have the following equation, which is of degree 8. It's got the product of 4 quadratic factors equals 0. So it's 0 equals x squared minus 3 times x squared plus 3 times x squared plus 1 times x squared plus 23. And basically we just want to solve this equation over various fields, in particular see what happens over the rationals q, and also look for the local solutions over all the q hat p, the p-adic rationals, and also the real numbers as well. And of course, to be a solution to this just means that you just have to be a solution to one of these quadratics equals 0, right? So you either have a square root of 3, so that's a solution to x squared minus 3 equals 0, or square root of minus 3, or square root of minus 1, or square root of minus 23. That's all it is to have a solution to this equation. Okay, so let's look at some of the local solutions and see what happens. Okay, we'll try to get rid of as many as possible first. So to do that, we'll look firstly over the p-adic rationals, q hat p, when p is at least 5. Okay, so what happens when p is at least 5? Well then, when p is at least 5, inside fp, the 3, the minus 3, and the minus 1 are all distinct elements, right? So I claim that one of these 3 has to be a square. So why is it that one of these 3 has to be a square inside fp? Well, the point is that, for example, if 2 of them are not squares, like this one, minus 1 and 3, if minus 1 and 3 are not squares, then the product by this lemma here has to be a square, and the product is minus 3. So there's no way you can have all 3 of them not being squares. So one of them is at least a square. So that tells you that over this finite field, we do have a solution to this. Okay, we're working in the affine case, so we're interested in any solution. Okay, so we do have a solution over the finite field. And part of the point of Hensel's lemma, and what makes it so wonderful, is that from that simple computation, you can get existence of solutions over the p-adic rationals. So we know that by Hensel's lemma, we find that there are p-adic rational solutions to the equation when p is at least 5. Okay, great. So we've done most of the primes, and we only have a few left. So let's look at the other finite primes, which are 2 and 3. Well, in this case here, what you can do is you can do the same sort of an argument. You check over the finite field of p elements, which is either 2 or 3. And in that case, you can see that x squared plus 23 has a root. Okay, so in other words, minus 23 is a square. So you can check that that's a finite calculation. And you can use a souped up version of Hensel's lemma to show that you also get a root inside q hat p in these two cases. And so there's only one case that's left. That's the infinite prime p equals infinity. So let's see what happens here. Okay, so how do we know that there's a real solution? Well, in that case, it's fairly easy. Okay, of course, all these quantities over here, they'll be positive for any real x. But this one here, of course, you can take the square root of 3 inside the reals is just the square root of 3. Okay, so x squared minus 3 equals 0 has a root in R. Okay, so the sum total of all this means that there exist local solutions for every p, both the finite ones and the infinite one. Okay, but what about a global solution over the rationals, v of q? Well, we can try to solve this not just over the rationals, but over the complex numbers. And what do we find? Well, for these three, you see, the roots of these three quadratics, the zeros of them are not real. The only real one is this one here, and that's root 3, which is not rational. So all the zeros of these quadratic factors are not rational, so that means that this variety, if you look at the solutions over the rationals, this is empty. So I hope you can see what's happening in this case, that actually it's quite easy to come up with a counterexample. And the reason why in this case is because there are 4 factors. So you can make the factors, each of them, they'll have some local solutions. So it's easy to get local solutions for all the primes. Okay? So for example, you throw in this factor to make sure there's a local solution over the reals, and so forth. But the point is that even though you have a local solution for this, it's not a rational solution. So if you allow lots of factors, then it's easy to come up with counterexamples. So really, the lesson to be learnt from this little counterexample here is the following. You should really only pose this question of which varieties satisfy the Hasse principle if it's what's called irreducible, in other words, you don't have factors like this, and also something called smooth, because this is also an extra condition which makes this, the variety is much better behaved when it's smooth. So this becomes a much more sensible question in this case. So remember, the first thing to do when you study a Diophantine equation is to look for local solutions, because looking for local solutions is a decidable problem. And then you can ask if there are local solutions for all primes p, whether there is a global solution. In other words, whether it satisfies the Hasse principle or not. So suppose you have all these local solutions, what do you do next? What's the next step in the theory? Okay, check to see whether it satisfies the Hasse principle. But how do you do that? Okay, well, one way is to consider what are called obstructions to the Hasse principle. Okay, so let's have another look and see how we framed our way of studying Diophantine equations. Okay, so one way to think about it is that the existence of local solutions to these Diophantine equations is a necessary condition for global solutions. Okay, it's a necessary condition, but it's not always a sufficient condition. When it's a sufficient condition, that's the time when the Hasse principle works. So you can ask, well, if it's only necessary but not necessarily sufficient, can you add in some more necessary conditions to make it sufficient? Now, of course, that's a difficult problem, and over the integers we have Matija-Savic's theorem, which basically says that that's not possible. Okay, but still, it's a good question. Okay, can you find new necessary conditions for the existence of global solutions so that you can try to get counterexamples to the Hasse principle? And such things are called obstructions to the Hasse principle. And it turned out, and this is the most famous example, is there is one such new necessary condition that was due to Manin in the 1970s, and it's called the Brauer-Manin obstruction to the Hasse principle. So it's named after Manin in particular, who came up with it, but it also uses the name Brauer, and the reason for that is that it uses the Brauer group. Now the Brauer group is something which classifies division rings over the field. So it's rather bizarre that to study this number theory, the theory of non-commutative algebra arises in this rather interesting way. But unfortunately, to talk about the Brauer-Manin obstruction to the Hasse principle, that would be a whole playlist in itself. I hope you enjoyed this adventure in pure mathematics.